Hi everyone. I guess I'm going to kick off the presentation session today. And I'm going to talk about my small project that I just titled Antworld because I was really interested in exploring this agent-based simulation side of artificial life. So that's like a little simulation that I worked on. So kind of the motivation for this direction, like as I was thinking about what I was interested in for this project, sort of taking in mind the main idea of the course that overall, like the idea of artificial life is characterized by this emergence of complexity from simple system components. Then we saw at the end of the course kind of this contrast between, at the very beginning, we saw Langton's ant, which was like one of the simplest rule-based models where this ant, I guess, should be moving in this grid, but you can imagine taking single-step updates and flipping the sign of the cells in the grid, and over many time steps, as you see on the right, this can produce these kind of complex patterns. However, like towards the end of the course, we saw with the introduction of the idea of agent-based models that you can trade off some things about scale for rule complexity. So if we have some agents in a system and we have some rules for interaction, we can also see the emergence of some kind of interesting and more complex collective behaviors, like in the case of an ant colony, where all of the agents are looking for example, a food source, and then through kind of indirect cooperation of actions, we see like an interesting optimized solutions emerging like for paths in the system. So that as a topic was interesting to me at the end of the course. And I think raises like some interesting questions about like the interactions of scale and rule complexity, sort of how this can be classified as or relates to true artificial life, and thinking about how we might include heuristics in those rules, and kind of in general, like what are those type of models useful for? So that, with that in mind, I wanted to look into, this idea of an ant colony as a type of agent-based model, where, as we kind of already saw in the course, the main idea here is that if we think about a single ant in this colony, it's moving in its world, leaving the nest and navigating, in the simplest case, first using some just random exploration in order to look for a food source. And along the way, it's leaving some pheromone traces that decay over a fixed amount of time that are indicating the path back to the nest. And if you scale this up to a colony size, you find, or you should find in this kind of simulation, that the colony can converge on shortest paths to the food sources, because given this fixed decay time, you get the shorter paths have a higher probability to be reinforced as multiple ants travel over and over. So kind of in this framework, my like overall goal and motivation for the project was to try to construct like a simple parameterization of these kind of agents that could be used for empirical exploration, to look at, say, for example, these trade-offs between scale and rule complexity, or how, just to think about how you could set this up in order to study the role of like these different parameters in the system. And I also, was motivated to try to use Unity, which is a game development software that has like a physics engine behind it, that is really useful and interesting for like pairing the logic with the visualization of the simulation. So I wanted to see kind of how far I could get with that. So given the setup, what this looks like is in my like first kind of naive conceptualization. I have my ant on the left there, that moves with some movement vector or heading direction, and it has some cone of sight where it might encounter different types of stimulus, such as pheromone traces of other ants, or food sources, or its nest. As it moves, depending on its state, which might be one of searching or homing, it would drop a pheromone, the blue or the pink, and these pheromones decay with a fixed over a fixed amount of time. And then, in this first naive implementation, I just take on each ant movement update, I sample a new random movement vector with some interpolation to to smooth the trajectory a little bit, and then add an additional steering to this random movement based on detection of the relevant pheromones. So in theory, having this exploration component, but then letting the ant be steered by the traces of other agents. And then what this looks like kind of in Unity, which was quite new to me, is the setup where you can work with the visual part of the simulation or the game. On the left-hand, on the left-hand column here, you have different game objects that then have different. You can assign components such as colliders or rigid bodies that allow you to control how your game objects interact with the physics of the system and of each other. And then you can attach control scripts on your game objects in order to set up the logic of the simulation. And then in practice, you have this ant colony that is leaving, as I mentioned, those pheromone traces so this is a few seconds after the start of the simulation. And what that looks like in practice was that this implementation was challenging in the scope of how I set it up. I very quickly ran into limitations of my system where I couldn't simulate more than 15 to 20 ants in the colony at a time. I quickly realized that there was a lot of room for optimization. I guess I could have known this beforehand, but this was quite a clear way to figure it out. So I see some kind of behaviors where ants are moving together, as you see there. But overall, within the confines of my setup, I couldn't recreate this kind of pathfinding optimization that I would have liked to see. But in general, it really it made me think about the choice and the interaction of the various parameters in the system in terms of the efficiency and memory constraints. On the one hand, I was creating for every pheromone, I have a game object, and that adds up really quickly when you scale up all of those pheromones for the entire colony. Again, there are it's made me think about design choices in terms of how to actually implement the exploration and the steering in a useful and efficient way. You can see maybe more clearly some of these kinds of small issues, if you just look at the one ant who is just exploring, encounters a food source, and then almost makes it back to the nest, but not quite. So obviously here there's room for more maybe a more thoughtful implementation in terms of, okay, maybe there can be some radius of detection of decaying intensity, like we've seen maybe in particle-based systems that I haven't implemented here. So to some of those points that I just mentioned, there's a lot of room for different types of improvements in this kind of a system, implementation optimization, and then choices about the complexity of the agents. For example, the pheromone signaling. I've just done this in a very simple way with this kind of cone sensor, but I know that there are other models that do this, for example, by using the two antenna in a kind of more sensory motivated way, where you might then have your rotation of your updated movement depends on the strength of different pheromones. And as well, even in the random exploration, there are kind of more physically motivated, maybe more realistic ways to implement this. And yeah, maybe because I come from more of a neuroscience research background where we study navigation in animals in terms of path integration, where animals can sort of accumulate over time like a history that lets them integrate the path back to the starting position or the home. So maybe that's an interesting addition to this type of model to consider, like in terms of the return to the nest, do ants have a path integration like mechanism? But then I think, again, it's interesting, it raises questions about how, when we continue to add like more complex rules or heuristics like this, to what extent is it an artificial life system if we really like kind of merge it more into like if we merge into more of a knowledge-based approach using these type of rules. And in general, also my takeaway is like, go play around with Unity. This was fun and interesting, kind of challenging if you don't have much experience in C#. That was quite time consuming. But yeah, I learned from that, and I would definitely recommend that it is quite, in general, quite user-friendly to pair simulations and interesting visualizations. And as a final point, what really like got me excited about these, thinking about these agent-based models or simulations is like why they're useful, and they do seem to be really useful, that you can kind of like get enough interesting stuff, or like you really get like useful complexity out of these type of models. Like what we saw already also in the course, like from the ant colonies, is that this type of simulation can actually like, be used to solve optimization problems. There's also like, I think like related classes of models that can be used to model like social phenomena. Like this figure that I take from a paper here has to do with like crowd response to a terrorist attack. So I think those are really interesting directions, and something I had kind of in the back of my mind was also like, I wonder like how explored the space of creative applications is for this type of model. And actually, as I was making the presentation and like finishing the project, I found what I thought was a really interesting paper that was applying ant colony simulations to artwork, and I gave examples for composing music and for painting with ant agents. So I thought those were really fun and interesting examples, and I'm very curious like how studied this space is, and like how these type of models relate to, I mean, I know there are a lot of existing generative models for music, for example, how those are related. So yeah, if anybody knows anything about this research area, I'm very interested to hear. With that, finish the presentation.
We have like 3-4 minutes for questions, if anybody has questions. Otherwise, I have a few questions.
I have a remark. So there's a conference called A Life in Copenhagen this summer, and they will speak a bit, I think, about this art thing also.
Yeah.
So I had a question about the kind of the more specifics of the algorithm.
Yeah.
So I was wondering, how did you implement the random exploration part, like to avoid the ant like going crazy? It seems that when we see them, they are kind of using a smooth. So how do you choose like a?
I mean, I start with a random movement vector, and then I sample a new random vector and apply an interpolation so that this becomes
from the previous one.
Previous one.
Okay.
So that this becomes kind of smooth.
Okay. Another question I had, if you go in slide 5, so you have this alpha.
Yeah.
So can you explain a bit more how do you kind of steer due to the pheromones, your speed?
Yeah, like, so the idea was to move based on this random movement vector, and then if on each update step, each pheromone is also checking if it's been collided with an ant of the correct state based on its tag. And then if that's like a relevant collision that's in the line of sight, then I would add to the movement, or it's basically adding a force that's directed between the ant and the pheromone.
I see.
And as I've written it here, my idea was that this could be like a parameter that you play with in terms of like, if you combine this random movement with the pheromone movement, and maybe somehow imitates like a noisy environment sampling.
So the pheromone part is adding a force. It's not directly shifting the speed vector.
Yeah.
Okay, I see. I see. Okay. And I had another question. So in the videos you show, it doesn't seem to quite work what we expect, what we want to find, like this pathfinding.
Yeah.
But it seems that the pheromones are very short-lived.
Yeah.
So did you try to play with kind of longer-lived pheromones, or?
Yeah, I did, but there again, like because of the way I implement it, it really like quickly runs into memory constraints because each
of all the
pheromone
objects
is its own key object, and maybe there's like I can change this to, or maybe an easier way to do the naive implementation would be to do like a coarse grid-based system that makes this easier. For example.
It's very hard, the agent-based models, it's very hard to.
So I just ran it on my laptop and not even on the computer. So.
No, I understand. That's very good. Okay. So if I have just a few, because we have 1 more minute, except if there are other questions.
I'm just curious, how do you deal with potential collisions of the ants?
So that's like right now I deal with that using the Unity physics engine, which basically when ants are rigid bodies, that they when they collide, they collide, they don't cross paths. And you can also you can change the parameters there for like kind of how much they would bounce if they collide, which I guess they shouldn't really bounce. Ants are not that bouncy.
Okay. Yeah. Okay, very good. So one very small comment, very quick, and then we go on to the next one. So I think that one thing that would stabilize, apart from the problems of optimization, etc., one thing that would stabilize the simulation would be that the pheromones, instead of acting as a force, act directly on the speed. Like they force the velocity of the ant to be some value with some randomness, because that's usually also in the course. If you remember, most of the models we had, it was always first order differential equation time, so it's only the speed which is affected. As soon as you go into acceleration, you always have this kind of relaxed movements, and it's very hard to have something which does not also. So that's just a general comment. And the last thing I wanted to ask is about the pheromones. I was wondering, so this is just about the presence of a pheromone. Does the intensity of the pheromone?
No, as I implemented, it doesn't, and they have some as it is now. They have some larger trigger radius that's larger than the radius of the pheromone. That if the ant enters the zone, then it's a yes or no.
Okay.
But that's the other
Perfect. Okay. Thank you very much.